Hello friends, welcome to CEC live lectures. I am Dr. Pavitra Bharadwaj. I am Associate Professor in Jesus and Mary College, University of Delhi in the Department of Computer Science. So friends, we have been taking up different topics and we have been discussing a lot of areas, particularly in the last few lectures of this series, we are talking about operating systems. So we have discussed different aspects and different functions of the operating system, like we have talked about CPU scheduling, we have talked about process management, we have talked about deadlock handling, and today we come to discussing memory management in this lecture today. So memory management, or memory as we all know, is a sentinel part of the computer system as such. Right. So the computer system, basically what is the objective or what is the purpose of the computer system? So the computer system, basically it processes or it executes the user's programs, and to execute a user program or to execute an instruction, the computer will require to store that the program or those instruction in some place, right? So therefore memory is very important, because whatever program, whatever data the computer is working on or intends to work on later on has to reside in its memory. So therefore memory is a very central part to the entire system. And now since we are talking and we are looking at operating system, and we already know that operating system plays a very important role in assigning memory to the processes, in assigning memory to multiple processes, and also dividing the memory between the operating system itself and the user's process, between the system processes and the user's processes. So operating system plays a very important role in managing this overall scenario of the memory management, right? So if we understand memory, how is memory organized? So memory, basically it consists of a large array of bytes, and each byte or each array, each element of that array has its own address, right? And CPU will fetch the instructions from the memory according to the value of the program counter. We've already done this a lot, you already are aware, must be aware of this, that how instruction execution takes place, right? So basically the CPU will fetch the instruction from the memory depending upon the value of the program counter. Program counter is a register in the CPU, right? Now these instructions, whichever the computer or the CPU is having, they may cause additional instructions to be loaded, or they may cause storing of some data or some other information to the different memory addresses. So if we look at this instruction cycle, so we understand that first and foremost the instruction is fetched from the memory. After the instruction is fetched from the memory, the instruction has to be decoded, and then the operands are fetched from the memory. So instruction is residing in the memory, the operands are residing in the memory, and finally the result which is coming after the execution is also going to be stored in the memory. So basically whenever an instruction is executing, the instruction, the operands and the result, for everything the memory has to be accessed. So when we talk about how memory is managed, or how things are happening with perspective to the memory, there are few very important aspects that we need to discuss, and these aspects we will be discussing in the course of this lecture also. So first, because memory is a very hardware bound subject, so we need to talk about the basic hardware and how memory can be controlled through the hardware, how memory is organized in the form of hardware. Then we will look at how the binding of symbolic memory addresses happen to the actual physical addresses. So we will be talking about the different types of addresses, that is also the distinction between the logical address space and the physical address space, how the address spaces are defined. Besides this, we will also look at memory allocation, what is, how memory is allocated, and what are the different ways and what are the different algorithms which are used when memory is being allocated to any process by the operating system. So, if we look at the first aspect of this discussion, so if we look at the basic hardware, right. So, we understand that the CPU can access the main memory and the registers which are built into the processor itself, right. So, CPU accesses the main memory or the registers directly if they are a part of the CPU chip itself. We all know that registers are the working memory of the CPU, that is, registers are very much a part of the CPU. Sometimes we also know that main memory is also sort of inbuilt into the CPU chip, right. So, we have some machine instructions which will take memory addresses as arguments, but no instruction will take the disk address. So, this is very important to understand that on any instruction which the CPU needs to work, the data and the instruction, they need to be in the direct access storage device. Direct access storage device means that it has to be in the RAM, it has to be in the main memory, or it has to be in the CPU register. So, whatever data is required, it needs to be fetched, because CPU will never access data from the disk. We all understand this, right. So, if data is not there, then it is to be moved there before the CPU can act on it, right. So, CPU registers, we all know, as we already said, that they are the working memory of the CPU, they are built into the CPU. So, therefore, they are very fast in access. So, therefore, one access of the data or instruction from the CPU register may take only one CPU clock. So, they are extremely fast, right. But CPUs can decode instructions and perform simple operations on register contents, so at the rate of one or more operations per clock tick. So, one pulse of the clock means that one instruction has been fetched from the CPU and it has been executed by the CPU. Whereas, if we look at how instructions are fetched from the memory, now when you are talking about memory, so what is involved? The memory bus will be involved, right. So, this, because of the involvement of the memory bus, the transaction of data between the CPU and the memory involves the memory bus. So, therefore, it will require multiple CPU clocks. This access of data from the memory will require multiple CPU clocks, and in this case, when there is no data and the data is still to be fetched, so the CPU or the processor will remain idle, because there is no data to complete the instruction, it is still coming in from the memory. So, what is happening? Because of this, the CPU is remaining idle, and this situation of course is absolutely intolerable, it is absolutely unacceptable, because what we want that the CPU should always have data available. So, the remedy to this gap or to this speed mismatch is that we put another very fast memory between the CPU and the main memory, and this will also reside on the CPU chip. So, this is a very fast access memory which is residing on the CPU chip itself, and this is known as the cache. So, now what is happening? The data is coming from the main memory to the cache memory and from the cache to the CPU register. So, what is the reason being that data can directly be read from the cache. Cache is like a direct access device for the CPU, right. Now, besides this is one aspect that we are looking at for related to the hardware. Another aspect besides the speed aspect is the protection of the data, right. So, we must protect the operating system from access by the user processes, and also when we are looking at a multi-user system, we need to protect one user's processes from another user's processes. So, what is there in the memory itself? We need to ensure that the user's processes do not start accessing the operating system, and also the process of one user does not access the data of the other user. So for this, protection needs to be provided, and this protection is provided by the hardware. Why? Because why from the hardware, why not from the operating system? Because operating system will generally not intervene between the CPU and its memory accesses, because when operating system intervenes, then there are further delays, there are further costs which are involved. So directly when things are done through the hardware, they are always much faster. So in order to protect this kind of mutual access of the user's processes or user processes and operating system process, there is a different kind of hardware approach which is used for this purpose, right. So what needs to be made sure? That every process will have its own separate memory space, that is separate per process memory space will protect the processes from each other. And it is also very important to have multiple processes loaded in the memory for concurrent execution. So when multiple processes are loaded, they are executing concurrently, then it's very important that we bifurcate or we divide the space which is given to each process, right. So what will happen when we have divided, when we have separate memory spaces, then we will have the ability to determine the range of legal addresses that the process may access, and to ensure that the process can access only those legal addresses, because we've already earmarked the space for a particular process. We have defined the range of addresses which can be used by a process. So if any process is trying to use an address which is not a part of that range, then we will immediately get to know that some fatal error is occurring, right. So we can provide this protection by using of two registers. Two different types of registers are used. The first register is known as a base register, and the second register is known as the limit register. So base, as the word itself suggests, it will store the smallest legal physical memory address, that is from what place, from what point the memory address will start, and the limit register will specify the size of the range. So for example, let us look at this example of how base and limit registers, they define the logical address space. So if this entire box, it represents the memory. So we have a particular area where you can see operating system. So this is the operating system area. This area is reserved for the operating system. The rest of the area is for the user area. So say for example, one process has its base value as 30040 and its limit value is 120900. That is, it can have the value from 30040 to 420940, because the range, the 120900 defines the permissible value or permissible length of the address that a process can hold. So now what will happen if this process will ask for a memory space or is trying to access an address space which is outside this range, that is outside this range of 30040 and 420940, immediately an alarm can be raised. So this is one way of using hardware, that is the use of base register and limit register to control the way the memory address space is being accessed, or how protection is given from one process to the other process or between the processes in the operating system. So the protection of memory space is accomplished because the CPU hardware will compare every address which is generated in the user mode with the register. So every address will be checked by the CPU hardware, and whenever an executing program in the user mode will try to access operating system memory or other users' results, that is outside the range of that particular process, then it will result in a trap to the operating system. That is, that will result in a fatal error. It will be marked as a fatal error. So this scheme of using these two types of registers, that is base and limit register, will give the user program, it will prevent the user program from modifying the code or data structures of either the operating system or the other users. So, this is one very important aspect of how hardware can be used for two different functions. First function is how hardware is being used to accelerate the speed of processing by the memory, and how hardware can be used, how the memory hardware can be used for protection of the access space between the user processes, operating system and the different other user processes. So, the base and the limit registers, they can only be loaded by the operating system. So, this is where the operating system comes into picture, because operating system has special instructions, special privilege instructions, right, and these can be executed only in the kernel mode. So, since only the operating system executes these instructions, that is the loading of the base and the limit registers, and that too in the kernel mode, the operating system can load the base and limit register, because these can be loaded only in the kernel mode, right. So, therefore, the value of these registers can only be changed by the operating system. The user programs are not allowed, they are prevented from changing the value or the contents of the base register and the limit register. So, the operating system in a way is having an intrinsic control over what values are stored, that is what values are given to each process. The operating system knows that which process will have which values of memory addresses. Now, hardware address protection, as we can see in this diagram, it is also very much done using the base and limit register, and how it works, how a fatal error is going to come. So, if we know that the base value or the base register will have the initial value or the lowest value, and the limit will define the total range, right. So, if the base value or the value in the base register, right, if it has to be greater than or equal to the address space, to the equal to the space, right. If it is not, then it means that there is a trap in the system and the operating system is going into a fatal error. Similarly, the values in the base register and the value in the limit register together, they need to be less than equal to the value in the memory. The total value of the memory should always be greater than this. They cannot exceed the total memory. So, if it is yes, then the memory access is given to the process. If it is no, then again an error is raised and the process is not allowed to access the memory. So, this is how the address protection is provided by the way of hardware. Now, another very important aspect of memory management that we discuss is the address binding, right. Address binding is a very important phenomena which we see in the case of many operating systems, right. So, we all know that a program which resides on the disk in the form of a binary executable file, it is in a form of a binary executable file on the disk. Now, if you want to execute the program, then it has to be brought into the memory and it has to be placed within a process, right. Only then the process or only then the program can start executing, right. Now, whatever memory management technique or whatever memory management strategy is being used, irrespective of that, the process may be moved to the disk and the memory during its execution. So, while the process is executing, it keeps on moving from the disk to the memory and vice versa. We have already done this, how CPU scheduling is done, how process execution is managed and how processes keep moving in and out of the memory and they are shifted to the disk. So, the processes on the disk which are waiting to be brought into the memory for execution, they form the input queue. So, on the disk also there is an input queue, and from that input queue processes will be assigned to the memory. Then again in the memory also the processes will remain in a queue. That queue is there for the processes to be assigned CPU for their execution. Anyways, that is a different thing, but here what we are saying is that the processes which are on the disk, they are those which are ready for memory allocation, they form the input queue. Now, the normal single tasking procedure, right, it is to select the process in the input queue and load the process into the memory, right, and as the process is executed, it will access the instructions and data from the memory. Eventually, the process will terminate and the memory that the process was using is declared available, right. So, this is the very simple process which was used. So, most systems, they allow a user process to reside in any part of the physical memory, right. So, address may be represented in different ways during these steps. That is, during what steps? During the steps where the process is executing, it is fetching and it is freeing the memory, right. So, it is initiating, it is executing and it is terminating. So, address in the source program, basically they are generally called the symbolic address. Source program means the source executable code, right. They are known as symbolic addresses because they have they are like a variable counter, right. Whereas, when you are talking about the compiler typically binds the symbolic addresses to relocatable addresses, right, and there is the linkage editor or the loader, right, which in turn binds the relocatable addresses to the absolute addresses. Absolute address means the physical address. So, each binding, whether it is the binding of the symbolic address to the relocatable address or the binding of the relocatable address to the absolute address, each type of binding is a mapping from one address space to another. So, we will talk about three types of address spaces. One is the symbolic addresses, then we have the relocatable addresses, and then we have the absolute addresses. So, classically if we look at this, the binding of instructions and data to the memory addresses can be done at any step. That is, it can be done at the step of compiling, it can be done at the step of the loading, or it can be done in the step of the execution, right. It can be done anywhere. So, if we look at compiling, right. So, before we actually look at this is an important diagram to see, which explains the process of program execution and where the changes are happening. So, if we have the source program or what we call as the object code, right. So, this is first going into the compiler. So, what is the compiler doing? The compiler is actually converting the program, it is actually translating the source program into the object program or object code. Then the object code is actually loaded by another program, another software which is known as the loader software. So, the loader software is actually going to load it into the memory, and then finally the execution of the process is going to begin. So, these are three different phases that we are talking. First is the compilation phase, in which the compiler is going to bind the processes. Then we have the loading phase, in which the loader is going to change the address or loader is going to make the mapping work, and then we have the execution phase, or during the execution when the mapping is going to take place. So, we will be discussing more about how the binding or how the mapping is happening in the course of program execution. Till then, please keep watching CEC. Thank you.